Welcome. My name is Marco Coisson and I am a researcher at the Italian National Meteorological Institute. In this video, I will show you how we calibrate a field probe, a magnetic field probe, in the range 1 to 20 millitesla. In order to do that, we need a coil that is used to generate a magnetic field, and this coil is the transfer standard from the nuclear magnetic resonance and the probe that we want to calibrate. It is the transfer standard because the coil itself has been calibrated with the nuclear magnetic resonance experiment in order to determine the proportionality value between the electric current that flows into the windings and the applied magnetic field. The measurement will be done in a volume where the Earth magnetic field is close to zero. And this is done thanks to a set of 3 Helmholtz coils along the 3 X, Y, and Z directions that are used to compensate the Earth magnetic field. The first step consists in compensating for the Earth magnetic field. Contrary to what many people expect, the Earth magnetic field is not constant over time. It is a vector that has components along all 3 directions in the space, X, Y, and Z, and its intensity and direction depend over time. So the compensation of the Earth magnetic field has to be done before every calibration experiment that we do. Because if we do it today and repeat the calibration tomorrow, the Earth magnetic field vector will have changed both intensity and directions. In order to compensate for the Earth magnetic field, we use a Flash-Gate 3-axial sensor. The reason why we use a Flash-Gate is that it is a sensor of magnetic field that is extremely sensitive to low values of the magnetic field. But also, a Flash-Gate is a kind of sensor that gives an absolute zero measurement. This means that you do not need to calibrate the Flash-Gate in order to measure the zero. And this is exactly what we want to do. So the Flash-Gate probe is inserted into the transfer coils, and all of this equipment is in the middle of the Helmholtz coils that will be used to compensate for the Earth magnetic field. In order to ensure the correct positioning of the Flash-Gate sensor in the center of the transfer coils and of the compensating Helmholtz coils, we have a laser that has been positioned once for all in the correct place and whose spot can be used to identify the correct positioning of the Flash-Gate. So if we switch on the laser and give it time to accommodate for the vibrations, we can check that the laser spot is in the middle of the cross that we have painted on the Flash-Gate, and that ensures that the position of the sensor is in the middle of the volume of the coils. The actual process of compensating the Earth magnetic field is done through a software that has been developed in-house. The software interfaces with a multimeter that has the reading of the Flash-Gate sensor, and through a switch can switch from the S component, Y component, and Z component of the Earth magnetic field measured with the Flash-Gate sensor. The software allows to change the current value that flows into the 3 coils the 3 Helmholtz compensating coils, in order to keep the residual value of the magnetic field measured with the Flash-Gate sensor below the threshold value of 30 nanotesla along all 3 directions, X, Y, and Z. Now that we are sure that the Earth magnetic field has been compensated into the volume inside the Helmholtz coils, the first step is to zero the electronics of the Gauss meter to which the unknown probe is connected. Now that the Earth magnetic field has been compensated, we can proceed with the operations to calibrate a transverse Hall probe that, in fact, is the object of this video. Now we have removed the Flash-Gate sensor, and my colleague is placing the transverse Hall probe in the middle of the transverse coils, so that the sensitive part of the coil itself is in the middle of the coils. The Earth magnetic field has already been compensated, so we do not need to check it again. But we check with the laser spot. We do with the laser spot the same thing that we did with the flash gate sensor. So we check that the probe is in the proper position. To proceed with the calibration of the whole probe, we have a software that we have developed in-house that automates several tasks. The calibration is done by comparing the reading of the unknown probe to the field values that we know through the calibration of the calibration constant of the coils that are there. We set different values of applied magnetic field, both positive and negative, and we do the comparison between the reference value and the value measured by the probe. To do that, the software allows us to set a current value that flows in the windings of the probes, of the coils, giving us a known magnetic field, and then the software allows us to acquire a certain number of readings of the unknown probe, for example 10, so that we can obtain an average value and a standard deviation. Once we have acquired the probe readings for all the applied field values that we want, we are ready to proceed with the actual calibration of the probe. In case we want to calibrate a probe at even lower intensities of applied magnetic field, we have another set of coils whose range is between 15 microtesla and 1 millitesla that can be placed in the middle of the Helmholtz coils to compensate the Earth magnetic field in place of the ones that we used today. For the rest, the procedure is exactly the same. Of course, the calibration constant of these coils is different, but is again obtained through the nuclear magnetic resonance experiment in order to calculate the coefficient linking the current to the magnetic field generated by these coils. Once all the data have been acquired, it is time to proceed with the final calibration step, that is the document certifying the performance of the unknown probe. Here we have a comparison between the reading at different applied field values, both positive and negative, of the reference coils with the associated uncertainty. Then we have the data of the unknown probe, the average value of the 10 readings at the same applied fields with the associated standard deviation that is used as uncertainty. And then the uncertainties are combined, the extended uncertainty is calculated, and the discrepancy between the reference value and the measured value of the unknown probe is calculated. The calibration is complete.